Hello, everybody. This is your speaker. Uh, Maybe Ahmad can do a test to help me set this thing
Okay.
up for screen sharing. Let me know if I'm even being heard.
Yeah, you're audible. I don't think anything's being shared yet, though.
And now I'm visible.
Yeah.
Yes, I am visible. Here it says share screen. Let me sanitize it. Is there any nonsense you don't want to be looking at? See if I can get rid of pop-ups. Okay. Mhm. That one. Okay. Now, you probably see my cover. What is time? Am I right? Uh-oh.
Yes, sir. We can
Yes.
see it.
Okay. Well, we have a few minutes to go. Is Ahmad online? We got 6 minutes to go. No emails from him. And just to make sure you see the one, you don't see the one that has all kinds of nonsense like future view graphs and stuff like that. You see the one that just shows one view graph.
We see a single slide that says, "What is time?" and
Right.
then your name,
And not my pretty picture.
not your pretty picture.
Oh, good. You notice I'm a little early. If I do flash by, I have on my Pi Day t-shirt. So you guys all have one day to prepare for the big event.
Thank you for the fair warning.
Um, I only see two of you. Is that all? There's only two of us on that are visible? I'm expecting an old friend of mine from MIT to be on here, but I don't see him yet. The other friend, so not so old. Okay. Oh, I have never done this before. I don't know what the protocol is. Is the host Ahmad supposed to appear? He's got a minute to come. Does
Yes,
anybody know?
Ahmad does run these things, so he is the one who is supposed to kick off the proceedings.
Okay, so we'll just wait till then. And I only see 5 names here. Are there a lot more? Maybe I just get a shortened display.
You might, since you're presenting. Right now, I see 10 people, and
Oops.
in spite of this being a talk on timing, we tend to get people late.
They'll miss my first jokes. That's horrible.
Oh, here's Ahmad, who is technically on time still.
Okay.
Hello, everyone. Yeah, I always attend exactly on time because the recording is like, since whoever jumps in, but then I know when I should cut it. And I never cut it. Anyways, great to see you, Demetrios.
Yeah.
All right, we have so-called quorum, so let's get started. So, welcome everyone to another OCP tap call. This is call number 96, and we have Demetrios Matsakis today with a presentation. As usually with the format, we go with a quick intro. So Dr. Demetrios Matsakis has been the chief scientist for Master Clock since 2019, when he retired as a chief scientist for the time services at the U.S. Naval Observatory, called also USNO. So in his 40 years at USNO, he worked on most aspects of precise timekeeping, served 16 years as a director of Time Service Department, served 3 years as the president of the International Astronomy Union's Time Commission, represented the United States in Geneva as a vice president of the ITU WP7A delegation, and chaired or served on numerous working groups. He is an editor for the GPS Solutions. He has published approximately 170 scientific papers, secured 1 patent, and co-authored an introduction to modern timekeeping and time transfer. His definition of time can be found on Encyclopedia Britannica's web pages. Also, he received his undergrad degree in physics from MIT, specializing in elementary particle physics. His PhD was from UC Berkeley, and his thesis was under Nobel laureate Charles Townes, involved building masers and using them for molecular radio astronomy and interferometry. Uh, Originally hired at the USNO in 1979, his first 18 years there were devoted to measuring variations in Earth rotation and observation using connected element interferometry and very long baseline interferometry known as VLBI. In 2021, he worked on improving the USNO's prediction of Earth rotation for GPS operation as a member of the VA tech faculty. And he has won numerous awards, including the Newcomb Award, which is the highest international award for science at USNO, and the Institute of Navigation's PTTI Distinguished Service Award. He has published 5 short stories that are admittedly science fiction, and his blogs can be found in masterclock.com's webpage. So, I mean, I have the honor to know Demetrios for a while, and he's a very respected person in the community, and we are honored to have him here to give us this presentation about what is time. So, with no further ado, Demetrios, the floor is yours.
Okay, well, that was plenty of ado. I got to apologize to everybody. I'm sorry I put such a long thing in there. I didn't know if I would read it.
Great. That's great. You're
All right,
well
get going.
decorated.
All right, so what is time? The short answer is I don't really know. Nobody really knows, but some people think they know, and I will talk about that.
Yeah.
First, I want to separate time from the measurement of time. What the second is, I do know, and that's the next view graph. And so this is the second is tied to a transition of the cesium atom. It has 55 electrons. Most of them lie in inner shells around the nucleus. There's one outer one. The electrons are all spinning. The inner ones cancel each other's spins out, and the nucleus has a spin. If the spin of the nucleus is aligned with the spin of the outermost electron, you have a certain high energy level. They want to be opposite. It can make a transition on down and give off energy in the form of radiation, microwave, 9,192,631,770 of those oscillations are 1 second. That's the definition of a second. Okay, and of course, there's a lot more that can be said about all this, but we're going to go on to what is time. Yes, I have a definition of time that's on the internet. That coordinate, which can be most simply related to the evolution of closed systems. I actually thought a lot about it before I gave it to them, to the Britannica. And you can see it's a very technical definition. If I was to do it now, I would probably do it a little close to Aristotle's definition, which was that time is a way to order events. I'd say it's a value of a coordinate that can be most simply related to a sequential ordering of events. But there's other definitions too. For example, St. Thomas Aquinas, along 1,000 years ago, wrote in his book, if nobody asks, I know what time is. If anyone asks, I know it not. And then he goes on to say in his book that therefore, he's not going to pay attention to anything anybody ever wrote before about time. He's going to figure it out for himself. And after several pages, he comes up with a definition of time, which is very close to Aristotle's. Now, okay, but there's other definitions. For example, a very modern definition, time is nature's way of making sure everything doesn't happen at once. Professor Wheeler, who you'll hear about later in this lecture, says he got it from the bathroom wall. And I believe it. He doesn't say who wrote it on the wall. And I bet you he was the one who did that. If you look on the internet, you'll find other people are given that quote, but I go with Wheeler on this one. You'll find out later in this talk that time and space are intricately related, so I should give you a Wheeler definition of space. Space is nature's way of making sure everything doesn't happen to you. Of course, the same cast of characters could claim ownership of that. Okay, now let's get on with the show. What's next? Isaac Newton, the first person to maybe the greatest scientist who ever lived, or the most brilliant one. In his Principia, he says this about time. Time flows evenly throughout the universe, which is more or less what we all believe intuitively. And this is a literal quote, the first part. The second part is my paraphrasing of what he says, which is that it was always going on. There was always time. He did many other things, as most of you know, and he got into some fights over it. He invented calculus. But he didn't publish it. For years, he kept it as a secret.
How can you invent?
And that's just the way they were in those days. He got answered by Leibniz, a German, who said, no, time is relative. And he had a very good reason for it, at least in those days. Otherwise, why did God choose 4004 BC to create the universe? Why didn't he choose it 13 billion years ago, or a zillion billion years ago, or a zillion billion in the future? God was a perfect being that did perfect things for perfect reasons. He would have had to have a perfect reason to choose that silly date. Well, and he also then went on to say that God was outside of time and created time when he created the universe, but it's all relative to God. And he got involved with this. He published calculus long before Newton did. And yes, his version is the one that's being taught today in the schools. Newton had a theory of light as well, which is going to be relevant to this discussion. You follow it. And he thought light was made up of little blobs of matter, corpuscles, that could have different shapes and sizes and spins, and different colors had different masses, different weights of light. Not that different than what Einstein got the Nobel Prize for. Robert Hooke, a contemporary, thought it was a wave, but he was outnumbered by Newton. Newton was so brilliant that even the poets wrote about him. Alexander Pope, for example, said, nature and nature's laws lay hid in the night. God said, let Newton be, and all was light.
How funny.
But science progressed despite the authorities, and eventually, like 150 years later, they decided that light was a wave. Here's a schematic of the wave moving in this direction. It's a wave of electric fields and magnetic fields. They go from maximum to zero to minimum as the wave moves along. These were codified in 1861, or the idea came in 1861 from Maxwell, who took some things that people had learned earlier in that century and which we all know now, and put it together. I'm going to explain that, what he did. What he did was write down 4 equations. They call them Maxwell's equations that show you how you can get light out of it. I'm going to tell you the definition, how I told my kids this when they were toddlers, so they could understand it. The first thing was changing electric fields make magnetic fields. That's how electromagnets work. Every 3rd grade, I think, is when the science fairs all have electromagnets. And changing magnetic fields make electric fields. That's how Hoover Dam works, and electric generators. I have apologies to any people who know the real Maxwell's equations and know there's a lot of detail in here. And Maxwell might be turning around in his grave to hear I'm putting it this way, but it's valid. And so he showed in his equations that changing electric and magnetic fields can switch back and forth indefinitely in some circumstances, and that would be light, making light waves. So that was his theory of light. And the clincher, the exciting thing was that the mathematics, just given what we knew about how these turn into each other, correctly predicted the speed of light. So he nailed it. This was the high point of 19th century physics. There's no doubt about that. But that doesn't mean that that answers didn't lead to new questions. People said, well, okay, it's a wave, but then there has to be an ocean for the wave to be in. And they called that the ether. And so for the next 50, 60 years, until Einstein came along, people were trying to figure out the properties of the ether. One person who did this was Michelson and Morley, the two of them. They tried to answer the question, well, how fast was the Earth going with respect to the ether? They set up an experiment to measure that, and they measured it for a whole year because they knew that the Earth is going around the sun, so it's going 18 kilometers per second one way, and 6 months later it's going the other way. And what did they find? 0. And this might be the only time that the Nobel Prize got given for discovering nothing at all. Well, there was another time maybe the Nobel Prize got given for lobotomies, but I would call that discovering something negative. So I'll stand by this statement here. Then the new people tried to explain this. How could it be, the Earth not be moving? We knew that the Earth goes around the sun and then it changes. So some people said, well, maybe the Earth doesn't go out around the sun. Maybe the sun goes around the Earth after all. But at that point, there was other evidence showing that couldn't be true. And some people thought maybe the Earth dragged the ether with it. And there were reasons to rule that out. The final explanation came when Einstein came along, and he tried to imagine what would a light wave look like if you were traveling alongside of it at the speed of light. So here's a light wave moving along. You're moving along with it. You're right here, say, and you see the fields at a maximum. Then as you move along, the fields move with you. You're always seeing them at a maximum. Or maybe you're where the fields are 0. As you move along, the 0 moves along, so you always see the fields to be constant. It would look stationary. Nothing would be changing. So Maxwell's equations wouldn't work. What's the answer? How can you explain this? His answer was very simple. You just can't do it. The special theory of relativity starts out with matter cannot travel at the speed of light. Let me get sorry about these cursors. In fact, nothing can go faster than light. And as part of this, all observers measure identical values for the speed of light, no matter how fast they're moving. These are pretty revolutionary things, but to make them be true, you had to distort space and time. And therefore, space and time get mixed up. And honorable observers, by honorable here, I mean physicists, engineers, and computer programmers, they'll disagree about what's stationary, how long length is, what's simultaneous, and how fast time moves. The saving principle is, though, that any physics freshman could compute what different observers will observe. So there's a special relativity all for you. We're going to talk about the different things later. Let's talk about what the freshman computes. He says a stationary observer will think a moving observer's yardstick shrinks, length is smaller, the mass is heavier. That's where E equals mc squared comes into this. He'll think the time runs slow and everything with it, including clocks. This actually was proven by looking at cosmic rays about 10 years after Einstein got going in this. But the real proof happened in 1971 when two people took atomic clocks from the Naval Observatory, put them in jets, flew them back and forth. And when they got back home, they compared the clock's time to the Naval Observatory time and found the traveling clocks had differed, just like Einstein predicted. Nowadays, you don't have to go back to experiments. You can just look at GPS. GPS is a 24-hour day in, day out experiment. It would not work if we did not correct for all the effects of relativity, not just the effects of the motion, but also of gravity, which is what I'm going to talk about next. But first, let me reiterate an objection that my brother gave to me years ago when we were in high school. He said, nothing can travel faster than light. How about if a cowboy's riding a horse and he shoots his gun? The bullet goes at a certain speed. If the horse is going fast, that bullet's going to go faster, right? And I said, yes, that's right. But if you have a modern day cowboy riding a modern day horse and he shines a flashlight, He'll think it's going at the speed of light, even though the car's racing along. And you too, in the outside on the grandstand watching him, will think it's going at the speed of light. Why is that? The reason is because, well, it's a postulate of relativity, but relativity also says that this bullet doesn't go exactly as fast as you might think it would be compared to how fast the horse is running. You can do the math, and it depends on, and you get almost the right answer, very close to the right answer, indistinguishable from humans, to it going a little bit the right, it's faster at the speed of the horse, but actually it's a little bit slower. And when the speed of the horse goes to the speed of light, then Einstein's equations again have the bullet only going at the speed of light. So it all works out. You just have to accept the premise that this is true and warp everything else to make that happen. Something remains to time, though, which is causality. He strips time down. He says events are what's real. They're the same for everybody. My talking to you right now is an event. And different observers can give them all kinds of coordinates in space and time. Doesn't matter. Those coordinates can be different. We can relate one to the other with our freshmen. But the events are still the same. So if you want to ask what came first, ask, did light have time to travel from event A to event B? In other words, can event A influence event B somehow? All observers will agree in that case about which happened first. Some will think they happen at the same place, but they'll all agree, even though all observers think they are stationary. If light did not have time to go from there, then event A in no way could influence event B because nothing can go faster than light. And the equations tell you that different observers will disagree about which happened first, and none will think they happened at the same place. In other words, time order is just causality. If something can cause something, it's earlier. And that's the end of the story for Einstein. Let me give you an example, a question, a quiz, a pop quiz. Which event happens first? Einstein gets the Nobel Prize? Or a star explodes in a large Magellanic Cloud 200,000 light years away. The newspapers say it took place 200,000 years ago. So the newspaper said the star exploded before Einstein got the prize. Let me hear from the audience. Which got it first? Did he get the prize first? Or did the star go off first? Not when we saw the star, but when it went off. Did I stump you? Well, you're not supposed to ask hard questions. So this is the question that no matter what answer you give, it would be right. Because some observers would think Einstein got the star first, got the award first, but other people traveling at a very high velocity in a certain direction will think that the supernova went off first, and then Einstein got the prize. The two observers' sense of time and space is totally different, just like the freshman would calculate. But all observers would say that when we saw the supernova, that was after he got the Nobel Prize. Okay, because obviously something from when he got the ceremony, the newspapers would go over and we could read them at the same time. All right, forget that comment. Let's go on because it gets worse. Just repeating, time order is inseparable from causality. Now Einstein took on the issue of gravity and time. And he thought about a question that maybe we only thought about when we were kids. Our mommies told us that gravity pulls on the apple and gravity pulls on the moon, and we could just accept it. I remember when I was a young boy telling my brother, what could be more logical than mass attracts mass? Well, lots of things could be. That's no proof. And Einstein came up with a concept of it. It's called the general theory of relativity. It took him 10 years to do it after he came up with his special theory. Special means no gravity is involved. General can have gravity or not. And to do that, he had to play with our concept of space. He no longer, we think of space as something empty that things move around in. Not for Einstein. Space could have properties. If space is flat, Euclidean geometry applies. That's how we think of it, right? That's how they teach it in school. Sum the angles of a triangle, you get 180 degrees, and that's all there's to it. And then you can prove many, many theorems. And the straight line has a definition, the shortest distance between 2 points. Light moves in straight lines. Euclid came up with that. It's a way to define a straight line too. And matter moves in straight lines too, unless it's accelerated by a force, which was Newton's contribution, his law F equals ma. Gravity is force with a force to Newton, just like electricity, but not to Einstein. To Einstein, gravity was curved space. In curved space, Euclidean geometry does not apply. Some of these triangles, angles, do not add up to 180 degrees. That's obvious. And the law of motion was not that things move in straight lines, but the straightest way possible, given that they're in a curved space. In space and time. He called that the principle of least action. Another way people call it is the law of cosmic laziness. And here's another example. Imagine a two-dimensional world now. There's nothing outside this sphere, and there's an ant walking on it, a two-dimensional ant. The ant keeps walking, and what she thinks is a straight line, but she ends up coming back to where she started from. We know how to explain it. How does she explain it? Gravity. There's a gravitational force. She thinks gravity makes her going in a circle, going in some kind of orbit around it. But we know that there's no forces involved. The space is curved. So Einstein replaced gravitational force by curved space and motions in curved space. This leads to things you all know about, so I'm not going to talk about it much, like black holes where space gets warped to a singularity. He also showed that time goes slower in a gravitational field. So, like in the movie Interstellar, if you go near a gravitational black hole but don't get sucked up and come back out, you will find that the whole world has aged a lot more than you have because time was slower when you were in there. There are billions of black holes that we know about, or in our galaxy, and in the universe. Wormholes are a parallel thing, but we don't know that any exist. In these, instead of going to a singularity, they go to an exit, to someplace else in space-time. They could be another universe as shown in this view graph. It could be our own universe. It's just some connection. We don't know how to make them, and we don't know how long they last. And some people say as soon as you go in them, you break them. But there's the wormholes. We'll talk about them in a minute. I'm going to go off now and give you a whole other definition of time, concept of time, of which Boltzmann gave the mathematical foundation to it. You might have heard of the Boltzmann constant, associating time with an increase in randomness, which he calls entropy. Entropy is really not exactly randomness, but it's a very close approximation. Let's take this example of a gas in a box. The gas is confined to the box. If I told you, we ask you which happened first, this one and this one grew into that one, or did it start like this and go into that? You'll all know that the gas might have started this way, but it ended up that way. This way has higher randomness because you can move particles around in here more and not change the overall properties than you can here. If you move a particle from here out to there, you've changed what you're looking at. That can't be done. You can only move them around within this confined area. So randomness is less here than is there. The progression of time is an increase of randomness. And this can get generalized in many, many ways. I don't have time to talk about it. I will talk about one paradox, which was Maxwell's demon. This is the same Maxwell who we talked about earlier, the Maxwell equations. He said, what if you had a box with a little partition in there, and you had a little demon there. And no matter how you started out with the configuration of the gas atoms, the demon could force all the gas atoms to be at one side by just whacking them if they were coming out and letting them pass through if they were coming in. Or the demon could do the other way. He could only let the fast ones go through and whack the cold ones so you get hot at one end and cold at the other. Well, what about that? Get that out of there. What about that? Doesn't that violate the rule that entropy must always increase? Just give me a little demon, time will still increase. So the entropy can't do it. And that actually had much debate about it. And it wasn't until, I think, the 50s when a computer programmer figured out the reason Maxwell's demon does not work. The demon would need to have some sort of memory. He'd have to remember enough to be able to whack the atom. If you give a demon that much memory, then he either keeps storing that memory, in which case it takes an infinite amount of it, or he has to dump the memory. The process of erasing the memory creates heat. That heat would have to go outside the box, presumably, otherwise it would heat up the box. So in order to keep entropy at a low value here, you're pushing heat and dumping it outside the box, and you're heating up the rest of the world. Just like an air conditioner. An air conditioner can make cold only at the expense of making the outside a lot hotter. So the law of entropy has not been overthrown, despite many efforts, including Maxwell's. Let me give you another way of looking at this and ask, does time have a unique direction? I show you 3 pictures of the same person in different stages of her life. You would say, oh, I know the order of time there. You see it. And yes, it corresponds with entropy because there's a lot more wrinkles on her face. It's a facetious definition of entropy. And probably, they probably put something on to smooth her face a bit for the picture. So you're saying this cannot possibly be that way order of time. But I'll say no. Because the other argument why you say it might be no is because this woman can remember being a kid, but cannot remember being old. But if you reverse the order of time, then when this woman, the old lady, becomes a young woman, as she becomes a young woman, she loses her memories. So at this point, she no longer has the memory of being an old woman. She still remembers being a kid. So the sense of time, the arrow of time, and the sense of randomness do line up. If you think what I was saying before was trivial or something, we're not going to go. It's actually something everybody agrees on. It's not arguable, at least in the scientific areas. But the stuff I'm going now is more speculative. I call it metaphysical time. There are people who have strong opinions one way or another, and they argue about them. I'm going to refer to science fiction a lot. And that's not a put down. Don't use that to put down the ideas. Remember that geostationary satellites and submarines and even traveling to the moon was all first put into science fiction before the scientists got a hold of it and made it happen. Let's talk first of antiparticles as a possible way of traveling in time. What are antiparticles? Well, every elementary particle we know has an anti one. There's protons, electrons, even there's antihydrogen, which is composed of anti-electrons and antiprotons. Their properties are just like normal, except they have an opposite electric charge. So that means they accelerate in opposite directions. When they meet, they annihilate each other, creating a gamma ray, which is a high energy light form. And this happens all the time. We see it at any atomic accelerator like Fermilab or CERN. We can even see them in cloud chambers. Are antiparticles time reverse particles? Well, Feynman, who we'll hear about again, said, yeah, they might well be. This is called the Feynman diagram because he used it in elementary particle physics to do calculations. Time goes this way, space goes that way. a typical annihilation event, an electron meets an anti-electron right here, make a gamma ray, it goes forward in time, and then it decays, gives off an electron and an anti-electron. That's perfectly believable. But Feynman looked at it this way. An electron comes along, gives off a gamma ray, and then starts going backwards in time. Because going backwards in time means it moves oppositely when it's subjected to an electric force, we think it has a positive charge instead of a negative charge, so we call it an anti-electron. And then over here, the gamma ray hits an anti-electron, gives it a jolt, just like in the science fiction movie Backwards to the Future, and he starts returning then into a normal electron. Feynman went further than this. He said, yeah, it's happening everywhere then. The electrons doing this, blah, 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 it's all happening. And take a slice of this one, which might go here and turn back, go here, and it goes here. You don't see it this way, but that one could also be this one, which gets hit by the jolt and then starts going forward in time and backwards in time. And that answers a very important question that people don't know the answer to, which is, why do electrons all have the same mass and proton, all elementary particles? Why do they have the same mass and the same electric charge, plus or minus? The answer is because they're all the same one. That may well be a perfectly satisfactory explanation for the physics. It might be valid, but it's not very exciting. And that's because we have a different sense of time travel that we like. Sexy time travel is time travel for you, but nobody else. Then you can go back and you can kill Hitler, or you can go back and create the perfect crime and then come forward to the future and get away with it. Or the other way, you can go to the future and commit the crime and then come back. That's the kind we want. So let's ask, does relativity enable that kind of time travel? And the answer is maybe, probably not. And the first one to look at it is these things called tachyons. They're elementary particles. They've never been observed yet, although people have made studies for them. If you turn on Star Trek, they're a standard feature. They're using tachyon beams all the time, so they exist in cyberspace. They're very unusual particles because they can only travel faster than light. They're allowed by the equations of special relativity. You just have to warp things a bit. You give their mass at the square root of -1, imaginary mass. And then Einstein's equations will give you these. They have the property that as they lose energy, they go faster and faster. So they can never reach the speed of light. If they gain energy, they have to gain an infinite amount of energy to reach the speed of light. Can they be used to communicate with the past or the future? There's a debate about this too. An interesting point, which is emitting a tachyon, so sending a message, looks like absorbing an anti-tachyon. That's going to come up again later. I'm going to have to leave this debate, though, to go on to other ways relativity might enable it. And this is that time travel can happen if there are what they call closed time-like curves. This possibility was done by Gödel, who was a good friend of Einstein at Princeton. You might know him for Gödel's theorem. He showed that any mathematical system will have things in it that are true but can never, ever be proven, and will have things that are false and can never, ever be disproved. He didn't know what they were, but he proved that those propositions existed. He also showed that with a particular configuration of space-time, which had an infinite hole of exotic matter, you could start out in one place, keep going forward, just like in this Escher diagram, and end up back where you started from. You can't get away from that. And people have since generalized it to even more, but even more configurations that could do this. But all of them require a kind of matter that we don't know now exists. This exotic matter it has negative pressure. Most matter likes to push out. This wants to push in. If you could make that, you could do it. There's another way, which came out from Carl Sagan, wiggling wormholes. Carl Sagan wanted to write a novel, Contact, and he asked Kip Thorne. Here's Kip Thorne announcing the discovery of gravitational radiation, for which he later got the Nobel Prize. And Kip Thorne said, yes, there's a way. So Carl Sagan put it in his book Contact, and they made a movie out of it. But I tell you right now, the book is better. It's not very long. You should read that and not see the movie. Up to you. Maybe you've done both like I have. Here's how you do it. You create a wiggling wormhole. You wait a little bit. Cross to the other end, get off. Let that wormhole wiggle. Get back on and go back. And you can return home before you left. You cannot return home before you created the wiggling wormhole, but you can return home before you crossed over. Well, all you got to do is make the wormhole and make one that will survive your going through it. Those haven't been done yet, but if you can make those, relativity lets you travel in time, which is then going to lead, if you could do that, that's going to lead to new problems. The most famous one is, click, the grandfather paradox. Okay, you can travel in time with your wiggling wormhole or whatever way. What happens if you go back and kill your grandfather 10 years before your father was born? Then there'd be no father and no you. That doesn't make sense. How can that possibly be? Well, Stephen Hawking, who some view as a successor to Einstein, thought about this, and he came up with a solution much like Einstein did for electromagnetic waves. He said, well, the reason is you just can't do it. He called it the chronology protection conjecture. So his conjecture, not a proof, is you cannot go back and alter the future. But that still lets you go back and fulfill the future. So here's a possible example. Here you are coming along, and all of a sudden, a time traveler, yourself, from the future comes back and gives you a great idea. You patent that idea, you go along, you hop into a time travel machine. Maybe it's an anti-you that goes back and tells yourself the idea. Okay. And then at this point, you're also going forward and you make a lot of money off your invention. This does not violate chronology protection, because you can see yourself going back. If you had the right way, you can see yourself traveling backwards in time as you go past through every moment of time to get back to where you were. It's perfectly self-contained. It looks great. You could do that. If you could make a time machine. But you could do a lot more. What happens if somebody else comes to you and says, hey, Demetrios, I got this great idea. And I say, oh, that is a great idea. I patented it a year ago. And then here I hop into the time machine, take that great idea and tell it to myself. And then I go forward still to get fame and fortune. Or do I? Maybe I'll get sued. I think I'm going to have to use some of my money to hire a lawyer. Well, let's leave the lawyers behind and go on and bring up quantum mechanics. I'm only going to take out of quantum mechanics what I need to talk about time. And these are two of the greats of quantum mechanics. Heisenberg set up the Heisenberg uncertainty principle, which said you cannot know both the position and the velocity to any accuracy you want, to infinite precision. Instead, there's an uncertainty. The product of your uncertainty in position and your uncertainty in velocity, which is equivalent to momentum here if you know the math, always must be greater than a number called Planck's constant, which is a very small number indeed. Bohr took that and he called it complementarity. And he said position is complementary to velocity. And then he generalized it big time, following the equations. He said, yeah, that works for the energy and for the lifetime. It really works for just about everything. And for example, in human life, if the guy comes up and says, I am here for you, the woman is exactly right. The question is velocity. Will he still be here for me tomorrow? And even on other things too, like a questioner once asked him, what's complementary to truth? And he said, clarity. And that's probably a very good answer. Let's go on with the show though. How does this lead into time? First thing it does is it leads you to unpredictability. Since you don't know what everything is, you can't predict things 100% future. You can't predict anything to 100%. You can only compute the probability. And it's always less than 100% and more than zero. It can be very, very, very good. Though, of course, it's very likely to happen. Einstein was very much against this. He famously said, God does not play dice with the universe. Yet it was shown by someone called Bell, it's called the Bell theorem, that you can do an experiment and show that physical properties do not exist. They just don't exist until they're measured. Einstein was wrong when he said that it's ignorance. There's nothing there, no reality until you measure it. There's not an unknown reality, there's no reality. 3 people got the Nobel Prize for the experiments that proved this a few years ago. It comes out to the multiverse now and the Schrodinger cat paradox. Here is time. Let's say you had a cat and you put it in the box and you had a radioactive element in here and a system set up so as soon as that radioactive element decayed, it would release poisonous gas and kill the cat, which you see here. You open the box just at the half-life of that decay. Then there's a 50-50 chance the cat will have died and a 50-50 chance you'll have saved the cat. The cat will be alive. The question is this, did your opening the box kill the cat if it dies, or would it die somewhere in here in the transition between when you set it up and when you opened it? The multiverse theory says that's a false question. Actually, both happen. In one universe, it splits into 2 universes. In one universe, you will have saved the cat. In the second universe, you open it, find the cat dead, and be cursing out Schrodinger. And since you're in both, 50%, you will see that as a 50% chance, but actually both happen. You're just unaware of the other one. Maybe you can do an experiment with some kind of a wormhole to connect the universes, but no one has devised one yet to do that. So this is beginning to break up time. It leads to the concept, does every possible now exist, since we can have the dead cat and the live cat? And in fact, Feynman, who we heard about before, showed that to do a quantum calculation, it'll require you to sum over all possibilities, no matter how unlikely or bizarre they are. For example, I'm giving this talk to you, and my girlfriend's going to ask how it went, and being a guy, I'm going to say, fine. You want to compute the probability that I'm going to say, fine. Well, you have to sum over every possible outcome that would lead to that event. For example, yes, I did lecture you wisely and you caught it all and you loved it. Or you hated it. You wanted to burn me at the stake and you walked away. You have to sum all these in a weighted manner involving imaginary numbers too, square root of -1, to get the probabilities. Another way to look at that is that time and space just impose order on an infinite set of possible nows. So there's all the possible things that could happen. They all exist all the time. An event is just defined when the atomic particles are near each other. And you order them, so the difference between consecutive events is minimized in a relativistic manner. And that order is what we call space-time. That's another possibility. So everything happens. If you commit the crime, you think you got lucky and got away with it? No. In some there's a world which you're caught and a world which you did get away with it, and they're all there. They're all real. The artists actually were ahead of us. This article here, this picture, sorry, nude descending a staircase came out in 1912, before quantum mechanics. So all that could be happening. And there's also another essence of unreality happening called virtual particles. Virtual particles, they come out of nothing and they disappear. They're allowed by the uncertainty principle. They violate energy conservation, but because it's for a short time, the violation times that. If it's less than Planck's constant, you're fine. The larger the energy, then the quicker they disappear. Is this real? Yes, we've detected their presence. This depicts something called the Casimir effect. If you have two plates and you bring them close enough to each other, they get so close that a large fluctuation like this can't fit. So they won't have those close to large fluctuations. You only have the small ones. There are more fluctuations outside than inside, and they'll be pressing against the metals and pushing them towards each other. That's a very hard experiment to do, to prove it, but it's been done. It's also been seen in something called the Lamb shift, which is the energy of the electron as it goes around the proton. So if we have all these things coming and going, what happens if we create a black hole and disappears? Inside the black hole, time goes slower. Space is broken up into the singularity. What happens is you get the quantum foam. It's defined on, they call it the Planck scale, very small in terms of size and time and weight and energy. It's giga-electron volts. At that level, space and time are broken up. They're not continuous, they're discrete, they're little pieces, which tells us that space and time are accidents of nature. They're just a human concept put on top of it. Just like the color is not a fundamental property. It just depends on what wavelengths of light it happens to reflect. All blue things are not the same. Music is not a fundamental property of sound. Maybe it's a better analogy. It's an emergent property. Sound is what's real. We decide to call it music. In the same way, space and time are not fundamental qualities. And because in black hole and space and in quantum foam, we know they have no meaning. So there's some deeper reality that's involved. Who came up with this? Our bathroom guy, Professor Wheeler. I once heard him give a talk. He was an old man. I was middle-aged. I remember going back to the Naval Observatory and telling a colleague, Wheeler's crazy. Doesn't make any sense. But he was right, like he always was. There's something deeper going involved. We don't know what it is. Now we're coming close to the end of the talk. We'll have to address some questions maybe with all of this, with our deep insights. Like, when did time start? There's two possibilities. It went infinitely back in the past, maybe, or the Big Bang, or could be. Or the Big Bang could have happened when two multidimensional brains, they call them brains, like maybe it's short for membrane, I don't know. They could have 30, 40, as many dimensions as you want. String theory requires many more dimensions to exist. So maybe when they collided and made our little four-dimensional space-time thing that we call the universe, or maybe we're somebody's science experiment. And these things aren't necessarily contradictory. Any of them could be going on. Time could also have started just now. Just now. Dinosaur bones, electoral politics, and all just started right now. In fact, there is something called Boltzmann brains, a whole theory about that, which I don't have time to go into. That's another possibility, but maybe more intriguing would be, when will time end? Newton said never. We thought maybe it could end when the universe collapses upon itself, but now we know it's going to expand forever, faster and faster. Or it could be when these two multidimensional brains separate, ripping the fabric of space-time. But more likely possibility, the most likely possibility, is time is going to end with a whimper. As the universe expands to a dilute gas. Let me explain this end of time. Here's the Big Bang in one picture. You see this all over now. I got this from the Wikipedia. This is now, that's 13.7 billion years ago when the Big Bang happened. In the very beginning, the first 10 to the minus 35 seconds, nothing was set. Everything was just a huge mess, and the universe was expanding exponentially. At the end of that period was when the strength of the electric field, the strength of the gravitational constant, the mass of particles, all of that was determined. At that point, the universe expands a bit, is expanding. It expands, it cools, atoms form. It's called a period called the Dark Ages because the stars were forming, and when they did form, we couldn't see them because there was hydrogen gas which would block the light. Eventually, the stars ionized the light, and we could see the birth of we could see stars. And the Webb telescope sees things from right here when we emerge from the Dark Ages. About here was the high point of star formation. Now we're making less stars, and we're expanding, and we now know we're expanding faster and faster. We don't know why. There are several theories as to why, but we know that it's a fact. And we know that the dark energy that causes it to expand has more energy than the mass of the regular matter and dark matter put together. So the outcome with the highest probability is space will expand faster and faster, and in a Google of years, and this is, by the way, the original definition of Google, we will lose contact with our neighbors because we'll be expanding so fast that the light from other galaxies or even stars, even though it's going at the speed of light, won't be able to make it because the space is expanding faster than that. Also, everything will have decayed, from black holes to protons. They'll all be gone in a Google of years. The observable universe will just be a dilute gas swirling. They call that a heat death, even though it's actually extremely cold as we measure it. There'll be no way to measure time, and therefore no way to have time. So this is what we're looking at, the most likely outcome of the future for us. Remember once I explained this to my sister, and the first thing she said was, "Oh, my books," but she published some books and she liked them. But I'm not going to leave you here with this because there might be some ways out. For example, Freeman Dyson, who wrote a great autobiography called Disturbing the Universe, I recommend it, came up with a way. First, you have to realize that we won't be humans as we know them now in a Google of years. Our minds will be mapped into whatever kind of matter exists, as is in many science fiction plots. But you can define life then as the ability to think thoughts, and we can use those thoughts to control avatars. There was a movie even called Avatar about it. So we might be living some kind of life like that in a Google of years. But thinking takes energy, and we have to release that energy as heat. Somebody's mumbling in the background. Is there a question, or is that just a cat snuck in? The Schrodinger's cat snuck in. Okay, no question. We can take them. I'm almost done. The brain equivalents have to always be hotter than the universe is large then, so we can dump the heat off into the universe. They also have to be cool because, as the computer people in this group know, cooler computers work more efficiency, and there's a physical formula to describe that, the greatest efficiency you can get, temperatures in it. So as the universe cools, that's okay. Our brain equivalents will get cooler. So how do we live forever then? With a given amount of energy, a fixed amount of energy, we can last forever because we think and use our thoughts to control avatars. Then we shut down until the universe cools enough to accept the waste heat. That's something like hibernating. And then we restart and go back to step one. And every step will take longer. Will take longer, but we'll still be able to think thoughts. And in the end, we'll have an infinite number of thoughts. So we'll have a form of immortality. There is a problem with this, in full disclosure. He came up with this theory before we knew the universe was accelerating. Now that we know it's accelerating, this formula breaks down for reasons I can't get into. So we're still stuck. There's in the end, we're looking at a cold heat death. No way to get Dyson can't help us. But science got us into this. I have every bit of confidence that science will get us out of it. First of all, realize that most likely does not mean very likely. If you flip a coin 100 times, the most likely outcome is 50 heads and 50 tails. But it is far more likely that you will not get 50 heads. You might get 51, 52, 49, far more likely than you'll get exactly 50. So this theory of the most likely could break down somehow. Here are some ways. We could have the wrong physics or new physics. Everything I'm telling you was unknown 200 years ago. Imagine what we're going to know in 200 more years. Also, the physics could change. The Higgs field has a current value of 256. It could spontaneously reset, changing the whole ball game. Maybe it'll reset to 42, like in the Hitchhiker's Guide to the Universe. My favorite theory, though, is Linde's theory of baby universes. As our universe grows, and especially when it was young, though, these vacuum fluctuations, it could create vacuum fluctuations that don't disappear. Instead, they detach, break off, and form their own universe. So yes, our universe might go off and die a heat death, but we have spawned many, many baby universes. Some of those baby universes, when they go through their period of inflation, they will not be hospitable to life, even as we don't know it. But some of them will. And so there will always be more universes and always be more life, and things will still continue. Also, there can be super engineerings. Maybe we can find a way to reverse the expansion by somehow. Or we could contact other parts of the multi-universe. Isaac Asimov wrote a great story about that, where they were able to do that to bring entropy back, get rid of their excess entropy and keep life going. It doesn't end up well, of course, but that's another story. In fact, that's the end of the story. My time's up. It's time for young people like Ahmad now to get excited by this and find a way to save the universe. If there's any questions, go for it.
Thank you very much, Demetrios. All right, so let's open the floor for some questions.
Well, I have a question.
Go ahead, Hisham.
What time is it now?
I can barely hear you.
Basically, Hisham said, what time is it now? So it's a timestamp.
I did tell you I could answer that.
Let's go for it then.
But that's my day job. So sorry, my ex-day job.
Let's turn off your screen share. So
Okay, let's see if I can figure that out.
be a button says share screen
Button
on the
up there,
bottom.
mute, stop video, new share. Well, I can still talk while I click. Maybe you can help me.
Just
Oh,
go
share, there it
with
is.
the mouse down on the
Stopped it.
bottom
Got
side.
it.
Yeah, got it. Awesome. Yeah.
Okay.
So yeah, let's answer Hisham's question. Basically, what's the time now? Like,
Well, you realize that does not have a very good answer.
yeah.
You can call it in UTC. So that'd be one thing if you want to know if you're daylight time or standard time. So it's a very complicated question. And also, you're probably at a different altitude from mine. And since time slows down in the gravitational field, if you're up on a mountain somewhere, your time will be different. So I'm not a freshman anymore. It'll be harder for me to calculate the difference.
Good.
So
Question.
you said
sorry.
time is ordering.
Sorry.
Go
Well,
ahead.
just 1 second. Let's see what Hasham has follow-up. Yeah. Hasham, go ahead.
I can go ahead. Okay. So you said time in distributed systems there is ordering and it is needed for consensus and other algorithms. So if we don't know what time is it now and there is no agreement on time, how in distributed systems we can define ordering of events?
You have to go, the relativistic approach to that would be that you can order the events if light has had enough time to travel from one to the other. It breaks down if there hasn't been time, and in your distributed system, then there will always be no exact way to order them. So if you're going to define time as a way to order events, then you can say, well, that's what it is, and I cannot tell you the time difference between these two events because I cannot order them. Of course, I could always be very nationalistic about it and say, I'm here in Washington, D.C. America is the greatest country in the world, which maybe you don't all believe, but I do. And therefore, our time is the time, and how I would order them using my coordinate system is the way it must be. I could do that, but that's just me talking off, probably saying things I'll regret. So it's there.
Right. Right. Roberto?
Yes. During the quantum foam explanation, you said, or you talk about two properties like not continuous and discrete.
That's right.
Just wanted to know if you could elaborate a little bit better, or well, not better, but because I didn't understood, or I want to understand it better. So, yeah.
Sure. So non-continuous, of course, means discrete time. If you just want to, you would like to imagine that between any two times, you could find the time in between them, but you can't if there's a black hole there, because time breaks off. It goes through a singularity. And what's the time inside of a black hole? You can't really measure that. And even if you had the time there, that through a particle, that particle is going to disappear. The gravitational field is going to suddenly change. And so the time at one spot of the quantum foam area will be different from the other, and the space. Just a bag of worms.
Thank you.
Right. Next. Michael, I think you are muted. Michael. Wait, Paul, let's go with you then.
Okay, Demetrios, thank you. And so I guess I have a frivolous question and I have a serious question. I'll put the frivolous question first so that we can let that brew. Are we on the inside of a black hole looking out, or are we on the outside of a black hole looking in?
That's a very good question. And there's something I have not talked about. First, I'll go into this, that we are like a hologram, that you can map everything in our three-dimensional world to a two-dimensional sphere. And we are just manifestations of things on this boundary, which is not exactly a black hole. And that could explain quantum entanglement, which I haven't really talked about, but these funny things involving quantum mechanics, they could all be explained by that, because experiments seem to show that locality, which means everything is determined within a small area, is not valid. So, yes.
Thank you. All right, and then the serious question is, what's your take on the recent work on indefinite causality? I'm going to put a link in the chat. This is someone, Julia Rubino and her friends have done a great deal of work on the theory originally from just over a decade ago by Károly Bruckner in Vienna, about this thing called indefinite causality. And it's basically superposition in time. Another way of thinking of that is time crystals. I prefer to think of it as indefinite causality, and the verification that's been done a few years ago, very recently actually, showed that this result is 7 standard deviations, which is actually way beyond a lot of the verification that you get at places like CERN.
I don't have anything to argue with all that. That time crystals are a very interesting type thing, and I can't give you any insights beyond what they're saying on that. So I'm going to defer on this one. It's a very good one. Very good question.
Right, thank you.
It's one of these things I wish would go away, but it might be the total story.
All right. Next. Michael, I'm not sure. Michael Imponente, if I'm pronouncing it right. You want to ask a question or something? Like, I think you're muted still.
No, thanks. Look, it was very interesting, this meeting. Demetrios, and it was very interesting, all of the conversation about
Thank you.
not so professional. Thank you very much. Bye.
Any more questions? So I have a question, Demetrios. I mean, when you look at like again your presentation, it looks like they're like basically. I mean, I have Professor Kinsner here who taught me about like this 2 school of thoughts where you have those who believe in time is quantized and those who think time is continuous. It looks like most of these things, they rely on the time is continuous rather than quantized. Is that correct? Or, I mean, both are theories, I mean, like, but just, they will have different consequences from what I was, like, what I wanted to add more. But first,
No, a lot of them could have time be quantized. And the idea that there's many fragments and space and time link them together, those could be quantized fragments, like the new descending a staircase. You put them together.
So now let's say, what if everything is continuous except time that is quantized, and that reflects in everything being quantized? Because everything we have, you look down in the fundamentals, there's always an assumption of time.
Yeah, it's hard to quantize time without quantizing space. So it'd be space-time that would be quantized. And
but what if you look at space as basically a second integral for, let's say, acceleration, which acceleration comes from energy, and then it's like from force and then energy, and then like you go back to time again. Like, I mean, could that be a possibility, or do we have like, I mean, things that are already taking this away?
I'm not aware of that. Going from an integral is no different than doing a sum, right? So
yes, exactly.
We go back and forth between discrete Fourier transforms and regular Fourier transforms, and we get the difference sometimes. Yeah, I don't see the issue there. That in order to quantize these things, you're going to need a very good experiment to verify it. Very high precision.
Almost impossible, because then we have to go to, like, I don't know, to the region of chronons, which, how do you want to measure them then? Something like that. Is that the case?
Yeah, something like that, yeah. The people have said, published papers saying that redshifts are quantized.
Yes.
On a scale much, but that's, I don't think anything's come to that. That's not believed now. That was an experimental fluke. That's a strong statement. I just haven't seen any publications for 20 years or so on it. But at one point I read them and saw it, and now we have much better redshifts in the universe, and no one's saying that.
Yeah, that can actually be something. If very interesting. That's very interesting. Anyways,
very quick question.
Yes, go ahead. Okay.
Thank you very much for a very illuminating and very insightful thoughts that you care to share with us. I really appreciate it. There's one question relates to what just Ahmed mentioned, the discretization. Would there be any usefulness for moving away from integer dimensions at the macroscopic level to fractional dimensions at the small Planck's levels? Is there any usefulness in terms of unifying certain ideas, including time? So there are new papers that are popping out that maybe at that level 1.51 dimensions are needed to explain everything, not even 2. String theory requires 10 or 11 to explain many things, but not all. But still, those are integer dimensions. Any comments on it? Thank you again.
Actually, I have seen speculations about string theory that needs far more than 10 to 11 dimensions, hundreds and hundreds and thousands of dimensions. Yeah, I have seen some references to fractional dimensions as well. There are people working in, but I have nothing to add to that.
Thank you.
So Maurizio, you have a question? Right.
Yeah, hi.
Oh, good.
Yeah, hi everyone. I just wondering if is it possible the concept of multiple dimensions of time, just like multiple dimensions, yeah, of physical one.
That's a good question. I've thought about it, what it could possibly mean and how you could have them.
Yeah.
Even Freud was writing a short story, a sci-fi, where the two things of time decouple and then you bring them back again. But doing it that way is no different than going into a gravitational field and coming back. You've just got one dimension of time. So the short answer is, it takes more intellect than I have to come up with an intelligent idea of how you could have more than one time dimension. I'd love to know about it if anyone has published on it, though.
Thanks.
All right, any more questions before we close up? All right, hearing none, we'll adjourn, and I will post Demetrios' presentation on the wiki, so with the recording, and we'll see everyone in 2 weeks by a presentation from Patricia about UTC versus UT1, the future for it, and again, thank you very much, Demetrios. So,
Bye.
All right, bye
Thank
everyone.
you. Thank you
Bye.
all. Bye-bye.
Thank you.